Hello, everyone. In last class, we just spent a lot of time, on taking a thorough review about this mutual exclusion issue. And in this class, we are gonna move on to the important and the difficult solution on this mutual exclusion issue. Also, semaphores can be used to control cancel of synchronization problems. So before that, we need to get through all of this content about the defects of the solutions with busy waiting. Also, we need to learn something about the wake up and sleep, these two basic system cores, and then we're gonna move on to semaphores, okay? So after we learned cancel of proposals to handle this mutual exclusion, you can find all of them they need the process to keep checking, to keep testing if the variable uh, is changed into the desired value. So that's called busy waiting. And if we choose such solutions to handle the mutual exclusion issue, there are some problems that we can't we can't solve successfully. For example, um, um, there is a problem called priority inversion problem. So after learning Peterson's solution and TSL or XCHG, this kind of instructions, which is supported by the hardware, you can see we can. It seems that we can control multiple processes to get into their own critical regions at different time, right? It meets all the four conditions. However, suppose such a case, if we suppose there are two processes, one is with the one has a higher priority, let's name it H, and the other process named L, which has lower priority. And if it's possible that sometimes the L is already in its critical region and executes some instructions. At this time, if the CPU switched from L, this process with lower priority, if CPU switches from L to L, it's possible, right? The process L will find that L is already, there is another process called L, which is already in its critical region. So according to the conditions, L has to wait, right? L just begins busy waiting to wait that L gets out of its critical region, and then H can get into that critical region, because no more than one process can stay in their critical region at the same time. But here is the problem, because L has lower priority and H has higher priority. if you if we learn something uh, in about the scheduler later, you come back and look at this slide, you'll understand that the process with lower priority, it can never preempt, it can never take CPU from any processes with higher priority. So it means as long as this process H with higher priority gets scheduled and starts busy waiting, it can never sorry, it can never wait wait for the L to get into the CPU again and gets out of the critical region, because L has lower priority. L has no chance to run any instructions after H. H is H is gonna use CPU all the time compared with L. As long as H is in CPU, L has no chance to get into CPU to run any instructions. So L cannot get out of the critical region because there is no instruction for L to run. L cannot get CPU to run any instructions. So this is called priority inversion problem, which can be caused by the solutions with busy waiting. So you can see this is not how to say, it's in a certain scheduling algorithm, it can cause such problems. So we will try to use another try to use another way to solve this mutual exclusion exclusion issue. As the busy waiting can also waste CPU time, because as I mentioned in the last class, if we choose busy waiting, it means the process needs to keep checking if the desired value is set. So this just wastes a lot of CPU time. And I just mentioned, if this process finds the value is not the desired one, it can just block itself. It can just set its state as blocked and wait out of CPU, wait for the value turning into the desired one. So this is called blocked wait. So we can use block to instead to take place of busy waiting when the process finds it cannot get into the critical region. It just get out of CPU. It won't keep staying in CPU to run repeatedly the checking instruction. It just gets out of CPU, and it will get out of CPU by call a spatial system call which is sleep. So this process, if he finds he cannot get into the critical region, it just makes this call to set its state as blocked and get suspended until another process wakes it up. So when does this another process wake the blocked process up? It when the time when the other when the process in critical region finishes its job, executes all the instructions in the critical region, this process will finally get out of the critical regions, and that's just the event the blocked process is waiting for, right? So when this process staying in critical region finally gets out of the critical region, then it will call this system call called wake up. This process is gonna wake up a certain process which is waiting for to get in its own critical region. So you can see this pair of system calls can help the processes get into their own critical regions one after another. No chance for them to get into the critical region at the same time. If there is already one process in the critical region, the other processes will call sleep to block itself until the process in the critical region gets out of the critical region, and then that process will just with the blocked processes up. Only one. Sorry, we're gonna wake one blocked process up. So we need to if this process needs to wake up another process, it needs to know some information about that process to be waken up, right? So there is a certain parameter. Maybe it's the process ID of that process. Anyway, we need to we need to provide the information about the process to be waken up. There is another way to connect the blocked process and the process to wake up the blocked one. We can use some parameter, or we can we can just put this parameter into the system called wake up, or we can just make sure that both sleep and wake up both these system calls each have one parameter. It just means you just connect them each other. They have the same parameter, so it means P1 and P2, they have the same parameter. Then when P2 needs to wake up some process, it just wake up P1. In the during the same time, in the computer, there might be a lot of pairs of processes. Maybe P1 is blocked by P2, and maybe at the same time, P3 is blocked by P4 because P1 and P2, they shared the same data, and P3 and P4, they are sharing another type of data, right? So P1 and P2, they should know each other. If P1 is in P1's critical region, P1 needs to wake up P2, but not P3 or P4. The similar things happen to P3 and P4. Anyway, you just need to know there are some parameters for them to record which one should wake up another one. So this is about the basic mechanisms of the sleep and wake up, these two system calls, and how to use it to control the mutual exclusion issue. We're gonna we don't put them in we don't how to say, we don't use this two system calls. We don't illustrate how to use this two system calls to control the mutual exclusion issue. We just need you to know that this pairs of system calls, they can control the process to be blocked and to be waking up later. So this is the way to take place of busy waiting. So what can we use with these two system calls? How can we use sleep and wake up to solve a certain problem? We just we have to introduce this typical interprocess communication problem, which is called PC problem, means producer and consumer problem. Also, it's also known as the bounded buffer problem. So it means you just imagine such a situation, two processes, they just share a common fixed size buffer in the memory. And one of them is the producer. This producer process is responsible to put some information into the buffer. And the other one is called consumer. And the consumer process is responsible to take the information from out of the buffer, and this consumer process maybe will use that information to do something later. Anyway, the producer process and consumer process, they just share this common fixed size buffer. So you can see this is a typical synchronization problem. If you recall the how to say the spooler directory we just mentioned in the last week, you can see it's a typical PC problem because there are multiple processes which might need to need to print out some files, and then each of them needs to put the file into the spooler directory, and the printer here is just the printer the process corresponding to the printer is just it's just like the consumer, right? And all the processes which needs to print any files on the printer, they just act as the producer, right? And they share a common fixed size buffer, which is called spooler directory, right? So you can see the producer, I mean, any process which needs to print any files out, it just needs to put the file into the buffer. I mean, they need to put the file into the shared spooler directory, right? And the printer just get one after another, get the files one after another and put them and print them out. So this typical PC problem, you have you need to understand this is the typical synchronization problem. And what's the essential points of synchronization problem? It's waiting. It means for the producer, if the buffer, I mean, if the spooler directory is full of the files to be printed, then no more process can put any new files into this spooler directory, right? Because it's already full. There is no space, there is no free space, no slot for any new files. If there is one more process which just throw its file into the spooler directory, you'll see that process will just use its file to overwrite a certain file which is already in the spooler directory, and this should be forbidden. This should be forbidden, right? So this is a problem. If any process needs to print a file into the shared printer through the spooler directory, and at this time, if this process finds that the directory is already full, then this process needs to wait. So this is about the waiting issue. The process producer needs to wait. Wait for what? There is an event that the producer is waiting for. This event means that the printer the producer the process needs to wait. The printer gets at least one file out of that directory and print it out. Then there will be a free slot for a new file, right? Before the printer print any file out, the directory is full of files. After the printer just prints it out, there is one more slot, one more free space for the for this process to put its new file into the directory. So this is a waiting point. Also, so for the producer process, it has to wait sometime at a certain point. And for the printer, it might be waiting for a certain event too, because if there is no file in the directory, if the spooler directory is empty, totally empty, no files need to be printed, then the printer, as a consumer, it has to wait until any process, any producer process puts any file into this shared spooler directory, then the printers can get the printer can get it out, right? So you can see during this procedure, the producer might wait for something to happen. Also, the consumer might wait for something to happen. Actually, the producer might wait for the full directory becomes wait for their some free space emerges for, from the full directory, and the consumer might wait for the empty some new files will be put into this empty spooler directory, right? So this is the typical producer-consumer problem. If you recall the printing problem we talked before, and this producer-consumer problem is a typical synchronization problem. I spent a lot of time on explaining this problem to you because we need to understand how to use the semaphore to correctly solve this problem. Also, we need to learn how to solve the other synchronization problem in the fifth section of this chapter, and this is very important for the operating system, and also difficult, and also very useful if you want to work as a software engineer, if you want to code, if you want to get involved into any development of application programs, because you will see for a lot of application programs, the synchronization problem, also the spatial synchronization problem, I mean the mutual exclusion problem, it's very popular because they might, it's high possible for them to share any data or files, and as long as they are sharing, they are reading or writing, they need to read or write some shared data or files. They need to control this problem. They need to use some mechanisms or the framework to make sure that no risk conditions emerge, and they need to control the execution order is the right one, according to the synchronization rules. So this is very important for you, especially if you want to work as a software engineer. And we so this is how to say, this is just the explanation of the problem we need to solve. And if we just choose sleep and wake up, these two system calls to solve this problem, you'll see that there is it's just they just face a fatal risk condition, because if we don't figure out another way to fix this code showing in the slide has some how to say, bugs or errors, because you can see there is risk condition in these two segments of code. It's just it uses sleep to block the process which causes sleep, and this process might be wake up if something really happens. It seems this two segments of code can work well, but if you dive into the code, you'll see sometimes in some certain execution order, it might meet the same race condition and might cause big errors. So let's see how to understand these two segments of code. One is for producer, which is responsible to put some items into the shared buffer. If you recall, the Spooler directory means this process needs to put some files into the Spooler directory. And the other segment of code is for consumer. You can connect it to the printer. So it needs to take the item out of the shared buffer. So, and you should notice these two variables. One is n, which means the number of slots in the buffer. Because as I mentioned, this buffer, this shared buffer is fixed size, right? So we just suppose there are 100 slots in the buffer, 100 free slots for the producer to put any items in. And also there is another important variable called count. Count means the number of items in the buffer. So you can say in the very beginning, before any code is executed, no matter it's from producer or from consumer, in the very beginning, there is no item, right? There is no item in the buffer. The count is 0. So the initial value for count is 0. And in the very beginning, nothing in the buffer. It means there are 100 free slots. 100 free slots for the items. So the initial value of n is set as 100 and the initial value for count is set as 0. This is the initial state of this program. And then you can see in the producer, it just produce some item and check if the buffer is full. If the buffer is full, it means there is no slots for this producer to put any item in, right? So it should call sleep to block itself. If we don't use system call sleep, then this producer has to keep running keep running the same instruction to check if count is not equal to n, and that busy waiting way just wastes a lot of CPU time. So at this point here, we just use sleep, the system call, to replace the busy waiting and save us a lot of CPU time. We don't waste any CPU time, because if this process cannot move on to the next instruction, you should get out of the CPU and give the CPU to another process. So this is the meaning, this is the point we use sleep here. And if you can see this process, this producer process is now blocked, right? So when can this process move on to the next instruction to insert the item into the buffer? It needs to wait for the consumer wake it up. You can see here is a parameter about the producer. We just adopt the first way to match the producer and consumer. We just put the parameter into the system call wake up. So as long as the printer or as long as the consumer just takes one item out of the buffer, it means the n the count will decrease, right? After that, if the printer, okay, so we just talked about the PC problem, not the printer and not the printer case. Okay, so if the consumer finds that the count changes from n to n minus 1, it means after this consumer take one item from the buffer, before the consumer takes one item from the buffer is full. So when the consumer finds the count changes from n to n minus 1, it means there might be a producer which is waiting, because here you can see, let's get back here, there might be a process which is blocked, which is waiting for the consumer to take at least one item out of the shared buffer. So the consumer will just make this wake up call to wake up the producer sleep right here. I just it's hard to draw the screen with the mouse, so it will just wake up this producer, and next time when the producer is scheduled into the CPU, it can just move on to the next line of instructions to input the item. It seems that for the producer, if you want to put any item into the shared buffer, you just check the value of count. See if it's n. If the buffer is full, then you just sleep and you wait for the consumer to take one item out, and the consumer will wake you up, and then you can move on to the next step. And after you put any item into the buffer, you need to check if the count changes from 0 to 1. If count just changes from 0 to 1, it means this producer just put the first item into the buffer. It means maybe there is a consumer which is waiting for this item, because consumer needs to take some items out from the buffer, and if the buffer is empty, then you can see if the buffer is empty in the consumer, it will block itself by calling sleep, right? So when the producer finds the count is changed into 1, it means there might be a consumer which is blocked, and it needs to be waking up by this producer. So then the producer which puts the first item into the buffer needs to be responsible to wake up the consumer, right? So in this way, you can see it seems that they can cooperate in a correct way very well, right? If it's full, then you wait until it's not full. If it's empty, then you wait. You call sleep to wait, to block yourself until the producer just wake you up. It sounds well, but if you check the code more carefully, you'll see the area I just circled with a red rectangle. It's just the critical region relevant to the shared variable count. You can see for this variable count, it's shared by the producer, both producer and consumer, right? It means there are critical regions in producer and consumers. The critical regions are the codes, are the instructions relevant to the read or write operation on the shared data, on the shared variable count. So this critical region relevant to shared count is not controlled. There is no action to control producer and consumer gets into control them to get into their own critical region at different time. You can see there is no such control. It means it might happen. It's possible for this two processes. It's possible that right here, just the producer executes this checking instruction right after the producer finds the count is 1 and it needs to wake up a consumer. Right at this point, the CPU might switch from producer to consumer. And as the consumer, while the consumer gets into the CPU and executes some instructions to check if count is 0, it's not 0. It's already 1. So it's just how to say, it won't sleep, right? So at this time, you'll see it's possible that when the producer wants to how to say, it's not the right execution order, which might cause a problem. Let me put it again. So first, let's suppose in the very beginning the buffer is empty, right? So let's suppose that consumer just execute first. So at the very beginning, the consumer will find the count is 0. And at this point, before the consumer calls sleep to block itself, at this time, the consumer is not blocked, okay? I'm not sure if you can see clearly. I'm drawing here this point. At this point, I'm drawing some lines here. At this point, right before consumer call the system call sleep to block itself, right before this, the producer just takes the CPU. So the CPU switches from consumer to producer and executes to this point. So here it finds that count is 1 and it needs to wake up the consumer, right? So producer just executes this action, executes this line of code to wake up the consumer. But the consumer is not blocked yet. Before the consumer block itself by calling the system call sleep, right before it, the producer just takes the CPU away. And when the producer tries to wake up the consumer, there is no consumer for this producer to wake up, right? But producer doesn't know. Producer just thinks, I just did the action. I just wake up consumer, and then I can keep putting more items into the buffer. But at the same time, consumer after that, the producer can keep putting the items into the buffer, while the next time consumer just gets the CPU back, the consumer will, at this time, consumer will continue to execute the system call. But after the consumer makes this call sleep, it can never be wake up, because the behavior, because the action to wake it up is already happened before the consumer blocked itself. So as the producers and consumers keep running, actually for consumer, it cannot run anymore because it's just blocked, right? So after this, the producer will keep putting the items into the buffer until the buffer is full, because no consumer can get any item out of the buffer, because consumer is already blocked here. No consumer takes any items out of the buffer while the producer keep putting the items into the buffer. So finally you can see the buffer will get full, right? Finally the buffer becomes full and the count reach n, and producer will block itself by calling sleep 2, and at this time producer is blocked. Core is full, no slot for them to put any new item. At the same time, the consumer is blocked. It is blocked too, right? Because it's thought there is no item. It will consider that no items for the consumer to take out. So finally, you'll see the buffer is full of items, but the producer is blocked, the consumer is blocked, and both processes are waiting for something which will never happen. Producer is waiting for the event that the consumer takes any item out of the buffer. But the consumer, at the same time, the consumer is waiting for that the event that the event that the producer gets put any item in. So this is a typical phenomenon called deadlock, and we'll discuss this deadlock in chapter 6 in more details. Right here, you just need to know that deadlock means a situation that multiple processes are waiting for something which will never happen, just as I explained here, right? The producer and consumer might wait for each other to wake itself up, but it will never happen. So you can see if we just simply use sleep and wake up, we can fix the problem about the busy waiting. We don't waste any CPU time by repeatedly executing the meaningless instruction to check some value of the variable. But if we don't control the access to the critical region, it just meets the same fatal risk condition too. So how to fix all of these problems? We can use semaphores, which is a very powerful mechanism or framework to handle this kind of synchronization issue or any mutual exclusion issue. So now let's move on to the most important part, one of the most important parts for this course, semaphores. As I said, maybe you need to use semaphores if you are familiar with C or C++, you might use these semaphores. If you are more familiar with Java, maybe you need to learn more about the monitor based on the principles relevant to semaphores. Okay, so let's just take a close look about the definition of the semaphore. Okay, you can see if we simply use the sleep and wake up, we can't solve the problem successfully because there is still a critical region, there is still risk conditions, even though we solve the problem about the busy waiting, but we can't solve the synchronization or the mutual exclusion issue successfully. The right way is to use right way is to use semaphores. So what is semaphore. Semaphore is an integer variable to indicate the situation about certain resource. Actually, semaphore relevance to three parts. The value of the semaphore and two basic operations on this integer variable, which is called semaphore. So you can see, first, the semaphore it's an integer variable, and this variable is used to indicate the situation about certain resource. What kind of resource? It could be data, it could be a variable, just as the X representing the ticket number, or the how to say, the count. The count is shared by producer and consumer, right? So that count can be set as a semaphore too. Anyway, a semaphore is used to indicate the situation about certain resource. This resource can be any data, any variable, or even any files, or even any hardware resources. Okay, any resource, in any kinds of resources. So what's the situation? What can the situation be? If the semaphore, the value of the semaphore is 0, it means at this time there is no available resource in the system. If it's a positive value n, it means there are n available resources in the operating system. If it's a negative value, if it's minus n, it means there are n blocked processes waiting for the resource. So you can see, if we set a semaphore based on the count, which is discussed in the last slide. On the last slide, because the consumer and the producer, they need to share this count to decide if they need to sleep, if they need to call sleep, or if they need to wake up if they need to call wake up, right? So for this shared variable called count, both producer and consumer, they can't read or write count in the same period, during the same period, right? If producer is reading or writing count, then consumer should stay out of its critical region. So you can see the count, the access, the right, how to say, the permission to access count can be represented as a semaphore, and we can use 1 to set to represent we can set the initial value of that semaphore as 1. And it means there is only one how to say, only one chance for the producer or consumer to access the shared count. If producer is using that count, then consumer cannot use that count. So this is, I'm sorry, I should set the initial value of that semaphore as 0, maybe. We'll see after we learn the basic concepts about the semaphore. We'll illustrate how to use the semaphore to handle the PC problem, the producer and consumer problem very soon. So here we just need to focus on the meaning of the semaphore. A positive value means there are n available resources, and a negative value means there are n blocked processes which are waiting for this resource. You just need to memorize the meaning of this integer variable in semaphore. Okay, and there are 2 more parts relevant to the semaphore. It's 2 basic options called down or up. And sometimes you can you can see P operation or V operation in other textbooks. Sometimes if we say PV operations, it means down operation and up operation. Down for P or P for down, they are the same. They have the same meaning. Okay, down means P means to apply for an available resource, and up means to you just return and return a resource to the system. And if before you if there is already a blocked process right before you return that resource, then in the up operation you might wake up that process. So let's just dive into the down operation and up operation to see what's the detail inside it. So in down operation, we'll just decrement the value of the semaphore addressed, and after we change the value as value -1, and after that, after the action, if we find the value is negative, then this process which does the down operation will be put to sleep, will be blocked. And if the value is not negative, it means you can move on to the next instruction. And for the up operations, it just do the opposite actions. It just increments the value of the semaphore addressed, and after you add one addressed, and after you add one to the value and find the value is 0 or less, it means, remember, when the semaphore is a negative value, it means there are unblocked processes which are waiting for the corresponding resources, corresponding to this semaphore. So if you do the up action and find the value is now 0 or less, it means right before you do the up operation, the value is a negative one, right? It means right before you do this up action, right before you do this up operation, there is already more than one process was sleeping on this semaphore, right? So after if you find the value is 0 or less, right? So after if you find the value is 0 or less, then you should wake up one from the queue, from the waiting queue. So this is the basic actions happened inside the down and up operations. You just need to memorize that we use down to subtract one from the value from the semaphore, because semaphore has 3 parts. One is for the value. One is for the value to represent the situation of the relevant resource, and 2 other parts are the 2 basic operations to change the value of the semaphore and do some extra actions if it's necessary. When I say it's necessary, means for down operation, if after the value is changed and the value is negative, then the process, it means there is no available resource for this process to use, because we use down to apply for some resource. This resource can be a very abstractive concept, or a variable, or the data, or the file, or any hardware resources. It's very popular. It's a general generalized concept. The resource here, the resource here is a very generalized, a very generalized conception. Okay, so when any process do the down operation on a certain semaphore, it means this process needs to apply for a resource relevant to this semaphore on this semaphore. And if the process can use the resource or not, it's up to the value of the semaphore. If the process, after the process does the down operation and finds the value is negative, it means there is no available resource for this process to use. Then the process which just does the down operation should be blocked, should be put to a certain waiting queue relevant to the semaphore. This is the actions relevant to down operation. And if the process gets the resource, if after the process does the down operation and finds the value is not negative, it means at this time when this process wants to use a certain resource and there is available resource, there are some available resources for the process to use, then the process just gets one resource and to use and go use it. After it finishes its job, after the process doesn't need to use this resource anymore, it needs to do the up operation on the semaphore relevant to this resource and to return this resource back to the system. And after the process does always say if the process does the up operations and it finds the value is 0 or less, it means right before the process return this resource back to system, there are already some processes which are waiting for this resource. As long as now you just return one, then you should be responsible to wake one of those processes up and put them and get them out of the waiting queue on this semaphore relevant to the resource. You just return this resource back to the system, and there are some processes waiting for that resource, and you should be responsible to wake one up. So this is the two basic operations, down or P operation, up or V operations. Down is used for application, is used for resource application. If you want to use some resource, you just do the down operation. If you want to return resource back to the system, you need to do the up operation. And both down and up operations, they will change the value of the semaphore of the integer variable and see if and check if any extra actions should be done. So that's the that's basically the most essential part about the semaphores. You need to understand the meaning, the meaning and the details, the inside the up and down operations, the basic concept and mechanisms relevant to the semaphores are very important. Also, you need to know that the execution of the up and down operations, it's an atomic action. So what's an atomic action? Atomic action means an indivisible sequence of primitive operations that must complete without interruption. It means as long as the first instruction is executed inside the down or up operations, it will just execute all the instructions inside that operations. So it's a down operation, and both down and up operations, they are atomic actions. They are indivisible. It means you don't need to worry about if there are any interruption right before it wake up. If they check the value is zero or less, and it needs to wake up some a certain process. And between these two actions, what if the process is get interrupted? If it get interrupted, it's just the same error just happens, right? We analyze this case a lot of times. The error just happens between you check the value and you do some actions to respond to that spatial value, right? Between this, if the interrupt happens, then errors just keep emerging. So we should know that for the actions in the in the down or up operations, they are indivisible. The down and up operations are atomic actions. They are not interrupted until all the instructions are finished. So this is very important because you have to know this is just one instruction. You can take it, you can view it as an instruction, although it has multiple instructions. But you just need to know it's an atomic action. It cannot be interrupted. It will finish its own job without the interruptions. So you can just roughly view it as an as instructions which cannot be interrupted. Okay. So now let's take a thorough look at this PC problems, which is solved by the semaphores. Okay, so we already know the problem description, right? There is a shared fixed size buffer, and the producer needs to put items into the buffer. The consumer needs to take the items from the buffer. So they have some waiting. There are some points that they need to wait for. If there is no item in the buffer, then the consumer should wait. If there is no slots in the buffer, then the producer should wait. So how to control multiple producers and consumers cooperate, how to control them to cooperate the job with this shared buffer. We can use semaphores. We can use semaphores to solve this PC problem, this typical IPC problem. So now let's dive into the code. Okay, before that, you need to memorize the relevant variables. So here, similarly, we set n as 100. So it means in the very beginning, there are 100 slots in the buffer, right? And we just set three different semaphores. The first one is very special. It is used to control the access to critical region. So you can see this just fixed the problem which happened in the case where you sleep and wake up, right? In that segment of code, we don't have any control about the shared count. We don't control the producer and consumer to get into their critical region. at different time. But here we use a special semaphore called mutex to control the access to critical region. So the initial value of mutex is set as 1. It means there in the very beginning, there is only one permission, only one chance for the producers or the consumers to access the critical region, to access the count. Of course, here you cannot see the count because the count is the value of the count is how to say is transferred or changed into into the semaphore, which is called full. So basically you can see here this semaphore full, which means the item, the number of the items in the buffer, right? In the very beginning, there is no item in the buffer. So basically you can see full here can be viewed as count, or we just we can just forget everything about the sleep and wake up and count about, forget everything about the last unsuccessful solution. We just take a new look right here. We just take a look on this new solution, okay? No more discussion about the old unsuccessful one. So we have 3 semaphores. The first one is used to control the access to critical region, and the second one is called empty. Of course, it just represents the empty buffer slots, the free slots in the shared buffer, right? In the very beginning, of course, it has 100. It has n empty or free or available slots in the buffer, and in the very beginning there is no item in the buffer. So for this third semaphore is set as 0. And then for the producer, you just need to know it needs to repeatedly produce some item and put it into the into the buffer and produce and put and produce and put that put. These are the basic actions for the producer. But you already know that there are some synchronization and mutual exclusion issues to be handled. So we need to use semaphores to control both the producer and the consumer to access their critical regions in at different time, right? So if the producer want to put any item into the shared buffer, it needs to do this down operation on empty first. Check here. So why does producer needs to do a down operation on empty first? Because the producer doesn't know if there is any empty slot in the buffer for it to put any new item in, right? It needs to check. It needs to check the value of empty. And how to check the value of empty? It's an action inside of the down operation, because after we check the value of the empty, and if the value of empty is less than 0, it means it is negative. It means there is it's not a positive value. It means there is no available, there is no free slot to put any new items in, right? So it will just block itself. it will put itself into the waiting queue on empty on this semaphore. So we should do this option first, do this down option on empty this semaphore first. When the producer do the down empty, there are two cases. In the first cases, the empty the value of the empty is set as empty minus 1, and the renewed empty value is greater than 0. It means it's a how to say, the renewed empty is not a negative value. So it means right before you do the down operation, there is available slot in the buffer for this producer to put any items in. Then in the first case, this producer can move on to the next line of the code, okay, to the next line of code. But in the second case, if the producer does the down operation, and after the empty is subtracted by 1, if the renewed empty value, not the old one, if the renewed empty value is minus 1, is a negative value, it means if you have to recall the meaning of semaphore. If the value of the semaphore is a negative one, it means there are some blocked processes waiting for this semaphore, right? Waiting for the resource. So you can imagine if this producer does the down operation and finds the renewed empty value is minus 1. So it means there is one blocked process which is waiting for the empty slot, which is waiting for the resource relevant to this semaphore empty. And who is this one blocked process? It's right, the producer just did the down operation, right? Because before this producer subscribe 1 from the empty, it must be 0. So the renewed empty could be 1. So before you does the down operation, the value of empty is already 0. It means there is no available resource relevant to this semaphore empty. It means what's the resource relevant to the semaphore empty? In this case, the resource relevant to the semaphore empty is a free slot in the buffer. So it means if P0, okay, if P0, this it's a producer process. If P0 does the down operation and finds empty is the renewed empty is minus 1, it means before it does the down operation, the old empty value is 0. Before P0 wants to use a free slot in the buffer to put any new item, there is no free slot new free slot in the buffer for P0 to put any new item in. So after P0 does this down operation on empty, the producer process P0 will be put into the waiting queue relevant to the semaphore empty, which means now the value of empty is -1, which means there is one process waiting for the free slots in the buffer. And this only one process is P0. And after that, if there is another producer process, we name it P1 or P2 or anything like that. You can see they will be put into the same waiting queuing on this semaphore empty, and the value of the empty would change from -1 to -2 to -3. Anyway, if there are -5, if the value of empty is -5, then there are 5 processes are in the waiting queue on the semaphore empty, which means there are 5 blocked processes which are waiting for free slot in the buffer to put some new items in. So I just explained the 2 possible cases. There are only 2 possible cases after any producer process does the down operation. Only 2 possible cases. The first one, it just gets the free slot and it moves on to the next one to try to put the new item in. The second one, it cannot get any free slot because it's full. Then it will be put into the waiting queue on the empty until some consumers just wake them up. We'll check this in the segment in the code inside the consumer, which is on the next slide. So here we just explain this line, and then we are gonna move on. So no matter which cases, because there are only 2 possible cases happen for this producer. Which does the down operation, right? The first one is just move on to it can directly move on to the next line. And the second one, it cannot directly, or it cannot move on to the next line immediately. It has to wait for a while and then be waken up by a certain consumer process. And then finally, in the second case, finally this producer will move on to the next line, right? No matter which cases, there are only 2 possible cases. The first one is directly, immediately move on to the next line. And the second one, you just need to wait for a while. And finally, you're gonna move on to the next line. Finally, the producer will move on to the next line, and the next line is another down operation. But this down operation is on mutex. So if you recall mutex, this definition of the definition on this semaphore, it's a binary semaphore because the initial value is 1. It means there is only one permission, there is only one chance for all the processes in the system to get into the critical region, right? It's very easy to understand, right? There are we just said this a lot of times. There are multiple relevant processes. They need to read or write some shared data or files, but at the same time, there is only one process which can stay in the critical region. So the initial value must be 1, which represents the only one permission to get into the critical region. So if the producer found that there is free slot. There are some free slots in the buffer to put a new item in. So the next step must be the concrete actions to put the item in, right? And this buffer is shared by the producer and the consumer. So you can see it's impossible to let the producer and the consumer let them read or write on the buffer at the same time, right? Not to mention the producer and the consumer. Even there are two producers. They both want to put some new item into the shared buffer. It's not allowed. It should be forbidden. Remember, if we should recall that example again, the Spooler directory. You remember, file A needs to be put into the directory, file B needs to be put into the directory 2. But if they both access the buffer, access the directory in the same time, some file, the A or B's file might be overwritten, right? We should control no more than one process is using the buffer at the same time, right? How to control this situation? Use this mutex semaphore. So the first down operation, it's on empty. It's used to check if there are free slots for the producer to put any new items in the buffer. And the second down operation is on mutex. It's used to get the only permission to access the buffer. Okay, no matter you want to you want to get something out of the buffer or you want to put something in that buffer. Anyway, there is only, anytime there should be only one process which is accessing, which is in this buffer, which is using this buffer, right? So we use the second down operation on mutex to get the only permission to enter critical region. You can see if here we suppose if right here, I just draw this point. If the producer 1 found there is slots, there is free slots, there are free slots in the buffer, and right before it wants to execute the next line, and the CPU switches from producer 1 to producer 2, and producer 2 will find there are wants to put the item into the buffer 2, because it's just if it just gets through the down operation on empty, it means there are free slots for both producer 1 and producer 2. But now both producers want to put some items into the same buffer, then there is only one can get the permission to do the real action, right? So if at this point producer 1 gets out of the CPU and it's producer 2 CPU producer 2 turn to use the CPU, and producer 2 will do the down operation first, and during the producer 2 is putting this new item in buffer, because this might last a while, because if you want to put a large file into the file, it might how to say, it might maybe it might last for a few milliseconds, right? Maybe. Anyway, during this period, when producer 2 is putting a new item in buffer, maybe the CPU is switches from producer 2 back to producer 1, and at this time, remember, producer 2 is already using the buffer. He it producer 2 is putting a new item in buffer. So when CPU gets back to producer 1, producer 1 will continue to execute the next line. It means producer 1 will do the down operation on mutex. And at this moment, what's the value of the mutex? Think about it, because producer 2 already did this down operation on mutex first. And after that, mutex just changes from 1 to 0, right? So when producer 1 gets the CPU back, when producer 1 does this down operation after producer 2, it will find the value of mutex is -1. So produce 1 has to wait at this point. So here, after, yes, very good. So you just understand the whole procedure, right? When producer 1 finish this down operation, producer 1 will be put into the waiting queue on mutex on this semaphore. Now producer 1 is waiting in the queue on mutex until, so producer 1 is blocked, right? It will get out of CPU. So maybe producer 2 will get the CPU back and finish the job to put the item in the buffer, and producer 2 will move on to the next line to do the up operation on mutex. So after producer 2 is out of the critical region, after producer 2 finishes its job, then producer 2 will do this up operation on mutex, and inside this operation you will see it will find the mutex changes from -1 to 0. It means there is a process on the queue in the queue on mutex, which is waiting for being waking up, right? So producer 2, after producer 2 does this up operation, producer 1 will be waking up by the up operation from producer 2, right? So you can see everything is going very well. It's in the right order. No more process, not only one process can get into the critical region to use the shared buffer. And if you keep digging the whole procedure, you'll see, because we just explained the details in the producer process, but the same analysis can be performed on to the consumer process, right? Because for the consumer, it has the similar problem. It needs to check if there are any items in the buffer. If the full is 0, it means there is no item in buffer. Then this consumer will be put into the waiting queue on full until some producer wake it up. Anyway, for consumer, it has to do this 2 down operations, both on full and mutex, and then after the consumer gets the permission to access the buffer, and also there are some items in the buffer for the consumer to get, then the consumer can move on to this line to take the item from buffer. And after consumer is done with this job, it needs to do this 2 up operations. right? And for this case, for the down operation, there are two cases. For any down operations, there are two cases. The first case is that the process directly gets what it wants and move on to the next one, move on to the next line of instruction. And the second case is that this process cannot immediately get what it wants. It has to wait for a while on in the waiting queue on the corresponding mutex, and finally it will get what it wants and move on to the next line, no matter which down operation. Down operation on full, down operation on mutex, they have the same two possible cases. Also, there are two possible cases relevant to up operations. Because when you change the value of mutex, in the first case, you just move on to the next line, because there are no blocked processes to be waken up. And the second case means you need to do some extra actions. You need to wake up a process after you found that the renewed value is negative or zero. It means before you return this resource relevant to the semaphore, before you return this resource, there are some blocked processes which are waiting for the process. And here in this on these two slides for this producer and consumer problem, we just explained a lot of times. Each semaphore is corresponding to an abstract resource. Here, for this semaphore represents what's the resource that the full is representing. It's items, right? The items are the resources, which is represented by full, and for the empty, for this semaphore, what's the resource represented by empty? It's the free slots, right? The resource is here corresponding to empty are the free slots in the buffer. And what kind of resource, or what's the resource relevant to mutex? The resource relevant to the mutex is only permission to use the buffer, right? So you just need to you just need to understand the meaning of semaphores, the three parts. The value means the number of the resources relevant to the semaphore, and the down operation means to you need to apply for a resource. Up operation is used to return the operation, and the different value of semaphores they have different explanation. Zero means there is no available resource. A positive number means there are n available resources, and if it's a negative number, it means there are unblocked processes which are waiting for the resources, or the resource. So that's the basic, very essential, or the key points you need to understand, you need to grasp when we talk about the semaphores. And this semaphores mechanism or the framework is very, very important for a programmer which has a strong ability. Okay, so that's all about semaphores, and we still have 2 minutes to just take a very quick look about the other possible solutions which can solve the synchronization problems in the system, such as you can use mutex to focus on the mutual exclusion issue. And for the mutex, you already see if it's set as a mutex, it's usually its initial value is 1. Means there is only one permission, and if it's 0 means there is no new process can get into the critical region, and if it's -1 or -2, there are 1 or 2 blocked processes which are waiting for entering the critical region. So this is about mutex. You can check some details about how to develop the mutex. There are implementation. Yes, in the textbook. But we just ignore those details. You just need to understand the principles. Okay, so monitors, how to say, it's a collection of procedures. It has the similar idea compared to the semaphores, but it's just the collection or the operations on the semaphores inside this monitor. So if you are interested in this part, you can check it after class. And Java, if you use Java, you can check the more detailed about this monitor. But some other languages don't provide this this framework. So maybe you should use semaphores. Anyway, so that's all about this class. We just put a lot of time, spend a lot of time on explaining the meaning of semaphores and how to use it to solve the problem, producer and consumer problem. I hope you can you can take a review, take a review after class, okay? And I have to say we are gonna take the exercise. We're gonna do some exercise in next class, which are relevant to the states of process and relevant to semaphores. So just be ready, get ready for that exercise in the class on Friday, right? Okay, so that's all for today, and I'm gonna send the messages about the exercise in the WeChat group too, so you can catch it in the WeChat. So that's all for today.